Hi, geometry students. This is Miss Graham, and today we are going to be looking at lesson 20-1, the Pythagorean theorem. And for our overall unit, we're going to be comparing the Pythagorean theorem and its converse. So this might be something you remember seeing in Algebra 1 or whatever math class you were in last year. We're going to go ahead and start pulling out pages 283. So pull out page 283. Through 285. Our first learning target for today is we are going to use similar triangles to prove the Pythagorean theorem. And the second one is we are going to apply the Pythagorean theorem to solve problems. Now let's look to the margin at the right to read what the Pythagorean theorem is again. So in any right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So if A and B are the lengths of the legs in a right triangle, so let's draw a picture to show this. So here is our hypothetical right triangle. And let's say we have A and B as the legs of our triangle. C will be the hypotenuse. So now what we're saying is that the square off of these, so B squared plus A squared will equal C squared. That picture might look a little bit familiar to you, but what we're saying is that the legs squared and added together will equal the hypotenuse squared. So that's why we get down here, C squared is equal to A squared plus B squared. So now let's go ahead and start relating this to our real life story problem. So it says Sarah owns an online company that manufactures custom kites. Her customers go to her website and design their own kites. Then Sarah's company builds them. Many of her customers don't know the correct names for the parts of a kite. Sarah is creating a web page to educate them so they can communicate better with Sarah and her staff. So because many kites include right triangles, the Pythagorean theorem is useful in analyzing the dimensions of a kite. So let's go ahead and start looking at number 1. It says the simplest kite is the diamond kite, shown below. When the sides of this type of kite meet at a right angle, you can use the Pythagorean theorem to find the length of the spine. So we can see here, this is our right angle for our two right triangles, and we can see they meet at the spine here. That's going to be our hypotenuse, whereas these two are our legs. So we can use the Pythagorean theorem to find the length of the spine if we know the two legs. So question A says, which side of triangle X, Y, Z, which side is the hypotenuse and which side are the legs? So go ahead, fill this in right now. All right, we should have what I have highlighted in red. That's our hypotenuse, side length XY, and then the sides are in green, which is XZ and YZ. So now it is asking us to use what we know up here, this formula of A squared plus B squared equals C squared, right, to figure out what is the length of the spine. So remember, we're looking for the hypotenuse. That's what we're talking about here. We don't know what it is. So I want you to go ahead and see if you can just start off by using the formula they give us, A squared plus B squared equals C squared. Again, we could also put C squared equals A squared plus B squared, doesn't matter. But I want to see if you can insert what we know, those two side lengths, into the correct spots, and then see if you can solve for the length of the spine. So pause the video right here to test this out. All right, let's go ahead and go over this. So we know our legs are 12 and 35, so I put those in for A and B. It doesn't matter which one you put for which first. Then I squared each of those values, and then I added their totals together. So that way I got 1,369 equals C squared. Now, in order to undo squaring, I took the square root of both sides, so you can see that within that step. So that way squaring and square rooting canceling out. And then when we put this in our calculator, the square root of 1,369, we actually get 37. So we know the length of the spine is 37 inches. So you're probably thinking, why are we reviewing the Pythagorean theorem for this unit? Well, it's now going to start to tie in together right below. It says, one way to prove the Pythagorean theorem is by using similar triangles. Oh, okay. So in the right triangle, A, B, C, so this huge triangle below, an altitude is drawn to hypotenuse AB. So this is our altitude. That's what we're talking about. it's drawn from the right angle to the hypotenuse, creating an actual right angle itself with how it's lined up. So this will form two new right triangles. So this will be one of the right triangles, and this is the other right triangle right there. They are actually similar to triangle ABC. So this is a lot of really good information, and this picture is something that we are going to see a lot in the future. So what it wants us to do below for number 2 is write a similarity statement for the 3 similar triangles. Now, we know that we have to make sure the correct ends are similar to each other. So I'm going to use kind of a highlighter to help us figure that out. But let's start off with triangle ABC. So we know when we're looking at triangle ABC, we focus on this right angle last, wherever that's placed. So I know I'm going to start off with triangle ABC, and when I'm saying it's congruent to another triangle, I have to make sure I follow that same order where I list the right angle last. Now let's maybe look at this triangle first. We have to discover the right angle, which, remember, if we know this is a right angle, this will also be a right angle. So I'm going to draw that in to kind of help us out. So we want to figure out, how do I list this angle last? And also, when I'm labeling this, I have to list the hypotenuse first, just like we did with AB. So if we want to list the hypotenuse first and also have this right angle last, we would say it's going to be similar to triangle ACD. So let's try that again. It's going to be similar to triangle ACD right there. So we're going to fill that in. It's similar to triangle ACD. And then we have our last triangle that we're going to look at over here, where we want to list our hypotenuse first. Well, let's find the right angle. This is our right angle in this triangle. We want to list the hypotenuse first. And we also want to make sure we list this angle last. So that means we're going to start off here and list it as CBD. So I'm going to go ahead and highlight that so that way we can see it's CBD. So it's congruent to triangle CBD. There we go. Now sometimes it helps a whole lot to redraw these, so that way they're all kind of the same direction, so that way it's easier to visualize it. I at least wanted to use colors so we could start it off here. All right, on to the next page. Let's go ahead and look at number 3. So it says the corresponding sides of similar triangles are proportional, just like what we said before, proportional. So you can write proportions involving sides of the triangles from item 2. So we're going to complete each proportion, then find the cross products. So we're going to have to actually refer back to our picture from the previous page. So what I'm going to do is I am going to copy and paste it so that way it's over in our margin right here. All right, so we have that pasted right next to us here. Perfect. And we have the similarity statements. So now we're going to look at the different lengths that are being represented, not the vertices anymore of our triangles. We're going to look at how they represent the lengths. So let's say we're looking at our big triangle. We can see that we have one whole length is A. It's actually between vertices C and B. And then you can see for our other side of our triangle, it's between vertices C and A, so that has a length of lowercase letter b. And between vertices A and B, this hypotenuse, it's worth a length of lowercase letter c. Now what we also want to do is we want to look at each of the individual triangles, our blue and our green one, and see, okay, what are the lengths of the legs and what are the lengths of the hypotenuse? So in our blue triangle, the legs are going to be worth h and x values, and then our hypotenuse is a b value. Remember, all these are lowercase. Then our green triangle, that hypotenuse is going to be a length of a, and then the legs are going to be h, and then c minus x. Now where we got c minus x from, since it's a little different from the other letters, is we took this whole length of c and subtracted that length of x. So now that we have a better understanding of, okay, the vertices are going to be used by capital letters, and our lengths of each of the hypotenuses, hypoteni, or the legs are going to be lowercase letters. So let's see, how are we doing this and comparing it to question number 3? So remember, we know corresponding sides of a triangle are proportional, right, of similar triangles. So what we're going to do is we're going to try to write a proportion. Now there's 2 ways we can look at a proportion. We can compare, like a fraction, the numerator and denominator, so that this could be, maybe a hypotenuse and a leg of one triangle. Something else we could do is we could compare a cross. So the denominators with each other, just like the numerators are with each other. So we could compare this way as well. Either way is going to work, but just for simplicity, we are going to start off by looking at just, a fraction form, numerator and denominator. So looking at this, see out of all our triangles, the red, blue, and green one, which ones have a side length of B and the same triangle has a side length of X. So go ahead, take a look at our picture and see what you see. All right, so looking at this, you can tell that our blue triangle, right, has a hypotenuse of length B and it has a leg, really the shorter leg of length X. So that's what we're going to be looking at right here. So we essentially have the hypotenuse. Let's try a pen. We have the hypotenuse right there, and we have the shorter leg right there. And again, remember, we're doing this with our blue triangle. So what we're going to compare across is we're going to try to compare the hypotenuse of one of the triangles and the short leg of that same triangle. Now what's nice is we have to fill in what the hypotenuse is. We really only have 2 options, the hypotenuse either of our green triangle or of our big red triangle. Now what gives us the clue for which one we fill in is this short leg. So we're using B again, so think of which triangle has B as the short leg. Is it the green triangle or the red triangle? That's right, it's the red triangle. So we know that we're filling this in with the red triangle information. So we can see that this is the short leg. So we want the hypotenuse of the red triangle, which is C. So we're going to go ahead and fill this in up at the top as C. So now I want you, ready? I want you to try to figure out how we can fill in this second one. We will do the cross products together. I'm holding on off for that second, for that step, but I want you to try to see if you can kind of find some comparisons and figure out what we can fill in right here. So go ahead and pause the video, do what we just did up here and see if you can fill in the missing information. All right, so just like before, what I did was I figured out, okay, what 2 sides I'm comparing. I ended up comparing C and A. That ended up being within our red triangle. C was our hypotenuse, A was the long leg. So looking at this, I had to figure out which triangle had A as the hypotenuse. It's our green triangle. So I knew the longest leg was going to be C minus X. So that was looking at our first step for number 3. Now, what it also wanted us to do right here was find the cross products. This is kind of that next additional step. I'm going to show my work below here because I really don't have that much room to show it right here. So what I'm going to do is I'm going to write down both of those proportions. So B over X equals C over B. And then I'm going to give it a little bit of space, and then down below I'm going to say A over C minus X equals C over A. So let's look at our first cross product. So that means we multiply the diagonals. So I'm going to go ahead and I'm going to multiply B times B. So that way I get B squared. And then I set it equal to the other products. Cross product, so C times X. So I'll set that equal to C times X, or I can just say CX. So now down here, I'm going to go ahead and do the same exact thing, but it's going to look a little bit different. So now, again, it doesn't matter which cross product you do first. I'm going to start off with A times A first, so that way I have A squared. And I know I'm going to set that equal to c times c minus x. Now, the tricky thing here is we're doing c times the quantity of c minus x. Wait a minute, this is going to require a little bit of that distributive property. So we're going to end up having a squared equals c squared minus cx. So the two pieces that we're looking at are this equation and this equation. Those are the two pieces we got. So that's going to build off into number 4. So it says use the equations from number 3, so those two equations, and we're going to use a little bit of algebra to prove that a squared plus b squared equals c squared. Well, let's look at this. Is there anything that you can see we can do, maybe a little, I don't know, substituting? Huh? That word probably sounds familiar, maybe from algebra class last year. Yeah, I see that. Oh, okay, there's a cx right there. There's a cx right there. Maybe what I can do is in the spot of cx, I could put b squared since they're equal to each other. So let's rewrite the second equation as a squared equals c squared minus, and then we're going to put down our b squared. Now, wait a minute. We want to prove that a squared plus b squared equals c squared. We want a squared and b squared to be on the same side, right? So don't we have to go ahead and add b squared to cancel that out? And then look at this. Voila! We then have a squared plus b squared equals c squared. Look at that. So the whole purpose behind these equations and setting up these proportions is to relate the idea that similar triangles and their proportionality does relate to the Pythagorean theorem. So we can see that math does build on. What you learned last year is going to continue to build on to this year and next year and so on. So let's keep reading on. Let's look at our check our understanding section. So here we're introduced to this idea of a Pythagorean triple. So a Pythagorean triple is a set of 3 non-zero whole numbers. So we're saying they can't be 0 and they can't be negative numbers. All right, they're whole numbers. There's not going to be decimals or fractions. So 3 non-zero whole numbers that satisfy the Pythagorean theorem. So what I'm saying is that we could come up with 3 numbers where if I put them into this formula, they will always work. Some of you might have seen different numbers before being performed in here. So what it wants us to do is explain why the numbers 3, 4, and 6 do not form a Pythagorean triple. So looking at this, think about this. If we came up with these 3 numbers, we should be able to put them into this equation and for it to balance out or make sense. So we know we have to put the biggest number as our hypotenuse. We always know that. So 3 and 4, those two will be the legs. So looking at this, let's say I wanted a little bit more room, all right? I'm going to go ahead and kind of go off to the side right up here. Let's see if I can get 3 squared plus 4 squared. Let's see if I can get it to equal 6 squared. That's why I kind of have that question mark right up above there. So we're having 9 plus 16. Let's see if it equals 36. Wait a minute. It does not. 25 does not equal 36. So this right here, this is proof as to why these numbers do not form a Pythagorean triplet, because it does not hold true when we use the Pythagorean theorem. So that would really be our explanation. So some of you might have already seen this. Wait a minute. Okay, I've seen the numbers 3, 4, 5 together before, and that has worked because 25 would equal 25. So that is an example of Pythagorean triple. 3, 4, and 5 together. Now, there's actually quite a lot of different triples that you can find if you Google on the internet, and that's something that we're going to come back to next week when we're looking at this lesson. So now that we got a little bit of practice at this, why don't we go ahead, and try a little bit of individual practice since we got some as a whole class. All right, let's go to the next page, and we're going to take a look at number 10, A and B. So let's zoom into that. Perfect. All right, so I want you to go ahead and try to find the missing side length. Now, I just want you to start with A because it wants us to simplify our answers in radical form. We might have to talk about that a little bit, but let's see if you can use what you know with the Pythagorean theorem to find, remember, this is a missing leg, not a hypotenuse. See if you can try that out. So go ahead and pause the video right here. All right, let's go ahead and talk about this. So because we're missing a leg, I have to put in 27, and it gives us 27 is going to be A. So I have 27 squared plus B squared equals 38 squared. Again, you could really use A or B spot. They just gave us that 27 was A. We don't know what B is. I mean, they might put X in that spot. Either way works, but go ahead and solving for B, we end up getting the square root of 715. We actually can't simplify that in radical form any other way. That is the simplest form, so that's what we're putting as our answer. B is the square root of 715 units, right? Maybe this is inches, feet, centimeters, but I like to always put units there. Remember, directions say simplify it and put it in radical form. Do not put the decimal there. Now, let's go ahead and try part B. So looking at part B, we can easily see that we got a right angle here. We know that this is a rectangle just from our visual right here. So we know that this is our right angle right there. All right, I want you to go ahead and see if you can find the hypotenuse. And then I want you to stop once you've found out what B is. We're going to talk about how to simplify your radical and just review how to do that again. So go ahead and pause the video, find out what our hypotenuse is. All right, your work should match mine. So I have my formula up at the top. I plugged in 1435. Again, it doesn't matter which one's A and B because we know when we square them and add them together, we still get 1421. Now, when I take the square root of that, this actually is, and I'm already starting to notice, I don't need that 2 right there. You took the square root of it. So I want the square root of 1421, 1421, and I have to figure out maybe what perfect square number is going to be divisible into this. What's the biggest perfect square number, right? Our perfect square numbers are 1, not really useful, but let's keep going. 4, 9, 16, 25, 36, 49. You could keep going and name it. What we realize is that out of 1421, it actually is divisible by 49. So we could rewrite the square root of 1421 as 49 times 29. So now looking at this, right, the square root of 49 is 7, and we can't take the square root of 29. So we know our answer is going to be 7 root 29, or 7 times the square root of 29. And we know we're going to label that as units because we're looking at length. Woohoo! So we were able to try these 2 problems looking at how to use the Pythagorean theorem to solve for different missing unknown lengths. All right, so now's the time of the lesson. We are going to check in with your teacher and see what your homework is for tonight. For Miss Graham's class, this was the homework, watching the video for today. So you can go ahead, head on out, and have a great rest of your day.